This is the third video of the specimen paper walkthrough. Number 6. A large number of runners took part in a 5-kilometer race. Here are some of the results for the runners. Here are the runners A to G and their race times. Maya wants to represent the results of all the runners using a stem and leaf diagram. Discuss 2 things Maya must do to be able to represent it in a stem and leaf diagram. So you're going to need prior knowledge of stem and leaf diagrams here. So I'm just going to work through the basics, and we're going to go through the absolute basics. Now, we're going to need a key. Now, key just basically decodes how you read the thing, and I'm just going to write this. So this would equal to 24, and you can see how it kind of makes sense where the tens columns are here and the ones columns are here. So I'm going to output quickly a stem and leaf diagram for you to just see, and I want you to spot the patterns and anything that you see within the stem and leaf diagram, and it will help you answer this question below. Okay, so now you see this. What are some things that you recognize from this? So if you know that 2 with the line and 4 is equal to 24, we don't need to really care about the units here. They will be given in the question or when you need to make one. But for now, we're just looking at the absolute basics. 2 with a line and 4 equals 24. So you can see for the top line of here, this will equal to 10 and 12, then 21 and 21 for the next one, and then 33 and 39, etc, etc. What you can see that these are integers and they're in the same format. They're not, for example, if you look at this, we've got runner A has 16 minutes and 24 seconds, and this one is 22:31, which I'd assume to be 22 minutes and 31 seconds. They're the same thing, but they're written differently, whereas in the stem and leaf diagram, they need to be the exact same thing, either a number or something similar. And that's basically one issue we're seeing, that we can't represent this in the stem and leaf diagram straight off the bat, because how are you meant to write 16 minutes and 24 seconds in a stem and leaf diagram without formatting it first? And so that's our first point, is that the data must be formatted, or a better word to use is cleaned. Now in this context, it could mean here, you can see this specific value for f is 30,57. It's just a misread or a mistype or whatever. So you just want to remove the comma and replace it with something else, or a colon, or whatever you format it into. And again, for A and E, you might want to remove the words and therefore make it into a nice integer format. That's what cleaning means, and it could also mean rounding it and rounding it to the same units perhaps. And that's another thing we must need to come to. If you look back at the stem and leaf diagram, what can you notice about everything here? So you look at all the data from 1 to 4, that's ordered, and if you look at all the data in terms of horizontal, it's going 10, 12, 21 and 21, 33 and 39, 40, 46 and 47. And they all go in chronological order, or they are ordered. So the data must be ordered. And there's 2 marks. Now I did touch on this earlier. Another point on the mark scheme is to round it to the same units. For example, here we can see integer. Now there could be some ways you might want to write it, for example, but here 19.2 minutes, well, that's not exactly the same as 16 minutes and 24 seconds. It would be more like 19 minutes and 12 seconds. And you can see it's 2 marks, so each one gets 1 mark each. Now for part B, we need to explain whether or not it will be appropriate to represent the results of all the runners using a scatter diagram, a histogram, and a time series graph. 3 different graphs that you need to know. It's not really too much to know, and you should just know these off by heart anyways. And one thing to know is a scatter diagram is simply a graph like this, and you have a variable on the x-axis, a variable on the y-axis, so there's 2 variables, and we call this bivariate data. Now let's go back to our table and inspect. Do we have bivariate data? It seems on the surface level we do. We have a runner and we have the race times. 2 variables, so far so good. It has our x and our y variables, which fits the need for bivariate data. But then you need to look at it in a bit more detail. What does runners actually represent? Well, this represents A to G, or the actual runners themselves. there's no numbers or anything attached to them. You could just replace these with names and it'd easily be the same thing. The race time, sure, you can actually plot these because you can plot these along the x or along the y because they're quantifiable, whereas runners aren't quantifiable. Sure, you might plot A here, then B here, then A, B, C, D, like so, but that's not quantifiable. So you're not really seeing the relationship between two variables. You're just seeing at runner A, they do this, runner B does this, etc., etc. You're not seeing a relationship because A and B are not related as the race times are. So it wouldn't be appropriate to use this. Now, a histogram, on the other hand, is a bit different. It's also another 2D graph, but on the side you have frequency, and on the bottom you have your class intervals or your class widths. Now, what are your class intervals or your class widths? Well, an example for here would be, well, if we look at our minimum, we have 16 minutes, and our maximum seems to be 30 minutes, so we could have 15 to 20, 20 to 25, and so on. Now, the point here is that this is continuous data. Continuous data is data that can take any value in a certain range, rather than discrete data, which is countable values. Now, as opposed to A, B, C, and D, E, blah, 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 being shown within the data, is kind of embedded in the histogram itself, like so. It's like, it's hard to explain in that sense because the data is just automatically included. The bars themselves represent how many. So if there were A and B were both inside, I don't know, let's say this range, then this bar obviously represents it because it's got a higher frequency rather than showing A and B specifically. Now the question is it appropriate for a scatter diagram needed to be bivariate data, whereas a histogram needs to have continuous data, as I mentioned earlier? And does this have continuous data? Well, time is continuous, and that is true, therefore we can say it is appropriate because it is continuous data. And the last one, a time series graph. Yet another one that you need to know. On the x-axis you have time, I wonder where that comes from, and then on the y-axis you need frequency. The idea is as the time moves on, you plot different frequencies here, here, and here, and then you join them up like so. Now, can we do that here? A large number of runners took part in a 5 kilometers race, and from here, it doesn't tell us, but I'm going to assume that they've done it in the same day. So I'm going to put that it is not appropriate as all data was taken in the same day. Another thing I want to mention is that it says that they take a race, and you do a race typically with each other at the same time. So even if you want to make the argument that the hours within the days, well, no, because they do it at the exact same time. It's just the same day is what it says in the mark scheme. Question 7. You should hopefully get by now that as you go through the paper, you'll see topics that you're not familiar with, and please go and revise those. And obviously, with the ones that you're confident on, just make sure to do some more questions. The table gives the simple index numbers with 2013 as the base year for the average prices of houses in Scotland and in Wales for the years 2014 to 2017. The table also gives the chain-based index numbers for the same information, and here's all the data, giving an interpretation of the simple index number 103.6 for Scotland. So if we look at that on the table, that is this value here, simple index number in Scotland. Now what does this mean? So now I'm going to introduce you to simple index numbers. An index number itself is where you compare something to the base year. Now a base year just means the year you want to start with. So right now it doesn't need to actually utilize this information, but you need to know that the base year is always given a value of 100 So base is equal to, well, the base value or the base year is equal to 100. So every other value is relative to the base value. So 103.6 is relative to 100, and we're told our base year is 2013. So if 2013 is the base year and 2014 is obviously a different value, then we're just going to see that whatever the difference is from index numbers from 103.6 to 100 is the difference from 2014 compared to 2013. So we can write this and we can see comparing 103.6 to 100, you can see there's a difference of 3.6. Now another thing I need to show is that the difference multiplied by 100, so you can kind of imagine this is a 103.6%. So the difference between these two gives us our percentage. So there's a 3.6% increase in house prices between 2013 and 2014. David bought his house in Wales for £165,000 in 2013. Using an appropriate index number to calculate an estimate for the price of his house in 2017. Let's highlight the key information. Here, Wales, the actual price, and we know that it's in 2013. 2013 is important here because that is the base year. What else do we know? Well, we want to find the estimate of the price of his house in 2017. So we're going to find 2017 on the table, so the 2017 column, and then we want to make sure that we're mapping it to Wales, which is in these last two rows, and then we want to, since we're still on simple index numbers, the whole thing is on simple index numbers, we're going to use this value here, 115, also known as a 15% increase. However, yeah, how do you write that as a multiplier? So if it's a 15% increase, and let's just attribute that to the 115 index number, they can also write a 15% increase as 1.15 as your multiplier. And so now the new price is going to be 15% greater than 165,000, or 165,000 multiplied by 1.15. I'm just going to type this into the calculator. And I get this value here, 189,750. Part 2 tells us to comment on the reliability of the estimate, and that's a key word there. So let's go back to the question. The table gives us simple index numbers for the average prices of houses in Scotland and Wales, and therefore the simple index numbers will be based on the average price increase or decrease, but here's increase. So if we're looking at the reliability of this estimate, well, just because the average house prices went up, David's house might have gone up higher, lower, it might have even decreased, or it might be the exact same. However, we don't actually know this, so what we can write is that the actual index numbers themselves represent the average increase in house prices. We can also write, however, the actual price of the house for his specific one may vary. Part C now, and we've come to our first proper large calculation question, and it's worth 5 marks. By finding appropriate geometric means, compare and interpret the yearly average change in house prices from 2013 to 2017 in Scotland and in Wales. I'm going ahead and I'm going to highlight the key information. Geometric means, compare and interpret. and the yearly average change in house prices between 2013 and 2017 in Scotland and in Wales. So yeah, the two sentences pack a punch and it has a lot of info that we need to digest. The first thing we need to look is at Scotland and Wales. So we're going to be looking at the table here and we're going to be identifying Scotland and Wales. Now we've done this, we need to find the appropriate geometric means. Now before I explain what a geometric mean is, we need to find which one this is for. So now we need to focus on another part of key information, the yearly average change in house prices. Now, whereas the first question or the first part was the simple index number which represents the change from the base year, here it's showing the yearly average change in house prices, which indicates we're using the year before the last. So if you're using 2015, the previous year would be 2014, and if we move to 2016, the previous year would be 2015. So, which one do we use? And here's another piece of information, is that the chain-based index number in this scenario, or in every scenario, is where you use the previous index number in your calculation. So these ones are the ones that we're interested in. In this context, the chain-based index number represents the direct increase in house prices from the previous year. So if we take this value, 101.5, this is a 1.5 percent increase compared to 2015, rather than obviously the simple index number where it's directly compared to 2014. So now we've got this information, we can actually start going about our calculations. And now we need to find the geometric mean. Now the geometric mean takes a formula, and that is as followings. Now, the formula is the nth root of each value in your sample set, or whatever you want to say, up to the nth term or the nth value, and then you just take the nth root of it when you multiply them all together. I won't go into too much detail here because this is something that you will need to cover, and if you don't know what I'm on about, you just need to go and learn it and revise it. However, it's kind of a different type of mean compared to the arithmetic mean. Anyways, we're going to use this formula and we're going to plug it in for our Scotland and Wales house price increases. So we'll start with Scotland. Okay, so if we look at Scotland, and that is everything in this row here, so let's just highlight it. We're looking at all of these. So basically we're just going to multiply each of these and take the nth root of it. And the n here is 4 because there are 4 years. So I'll go ahead and I'll write this all out. And I'll go ahead and I'll type this into my calculator. And I end up with this value, 103.23172 blah blah blah, and this is the equivalent of 3.2317 and so on percent increase. I'll round it to 3 significant figures, so I'll do 3.23% increase. Now I'll do the same for Wales. I have to apply the same formula, so it will again be the fourth root, and let's go to the table and we're going to look at all of these. I'll then multiply them together, take the fourth root, as yet again there are 4 values for 4 different years. And I'll type this into the calculator now. This gives me 103.54707 and so on. And if I take this as a percentage increase, this is the 3.547 and so on increase compared to the previous years on average. And so this, to three significant figures, is 3.55%. And I'll indicate that here. So 3.23% increase. So for Scotland, I'll write that 3.23% is the yearly average rate of increase. And I'll do the same here for Wales, and for Wales 3.5% is the yearly rate or the yearly average rate of increase. Okay, so now I've found the geometric means, and I've also found and I've done it for Scotland and Wales. Now we need to go to the compare and interpret. So we need to compare these. The values we've got are 3.23 and 3.55. So we need to compare. Now the easiest thing to do is just compare which one is bigger, and that is Wales. So Wales, which has a 3.55% average yearly increase, is greater than Scotland, with a 3.23% increase. Now, what does this suggest? That the yearly average rate of increases in Wales was greater than in Scotland. So I'll write that down now. Now that was a not difficult but a tedious question. It was 5 marks, so it was kind of worth it. I'd say it's a good question overall. You just need to know the formula for the geometric mean. You need to identify that is for chain-based index numbers, plug it in, find the values, compare and interpret, and it's basically packed into these 2 sentences. If you can break it down properly, then you'll have no problem getting all 5 marks. Question 8. Stacy is the manager of a large company. She wants to investigate the differences between the number of days of holiday taken by employees in different age groups. She obtains the following information about the ages of the employees. And here's the data, and we need to assess the suitability, taking a sample of 20 employees stratified by age and by gender for her investigation. Again, we'll just highlight the key information. She's taken a sample of 20 employees and she's actually stratifying them. I have a video on stratified sampling, so if you don't know what it's about, I'd recommend watching it. In a nutshell, it's just proportionate sampling of the population in your samples or your subgroup. So, what is the suitability of 20 employees stratified? Well, we can kind of see that there are a large number of employees here in total, somewhere roughly around the 300 mark, around that part. So if you're taking a sample of 20, the sample size is a bit too small, so we could write that as the point. But if we're looking at it from a different perspective, we could actually say that this is suitable. And why is that? Well, this actually fairly represents all of the groups, and so we can say that it's representative of the population. So and because of that, we could also say that it reduces bias. And another thing you need to know is that when you stratify a sample, you use random sampling to actually gain that sample. So it will reduce bias because you're not actually subconsciously picking one person over another, you're doing it randomly. So we can also use that as another point. Now if you like, you might want to add a connector just to make it smooth flowing. So you can see that there's 1 mark from the top and 2 marks from the bottom. If I check the mark scheme, what else does it say? You could say that it's not appropriate because you shouldn't stratify by the variable you're investigating, and here that is age, which is true. and it would be better if they stuck to one, for example, just gender.